This is the first session of a series of 3 lectures on nested interval theorem and its applications. I will state the nested up interval theorem. I will not prove it because that is already contained in one of my lectures on real analysis. The tricks which are used in nested interval theorems can be generalized in a large in more general context also. So it's an important tool for analysis. So I just decided to give 3 typical applications. So let us get started. Yeah, the references are my book on analysis, Ajit Kumar and his Kumaration, a basic course in real analysis. Indian reprint is available. You can also look at this article of mine which deals with this precisely. There I even give a proof of nested interval theorem using LEB property of real numbers and then give lot of applications. I'm not going to talk about all the applications which are in that article. You can download it from this site. Okay, search for it nested interval, and in this site there is a search facility. You will get it. You can download and read it. And as I said, it contains about 6 applications or so, but I'm going to concentrate only on 3 which are very basic and needed in real analysis. Okay, we are trying to prove 3 results from real analysis using nested interval trick theorem. So this will be a very useful trick. Okay, so let us get started. So what does the theorem say? So I have Jn, okay, which is closed and bounded interval, and for every natural number n I am given one such, and I say it's nested. It's a nested sequence. Look at the sequence. This is nested. What do I mean by that? That means for each n, Jn plus 1 is contained in Jn. So I have this like Jn plus 1 will be somewhere here. This may be my Jn plus 1. Okay, this may be my Jn. This is my Jn, and this is my Jn plus 1. Okay, so we also, this is good enough for us to conclude what it says. Then the theorem says, let me change the color, then intersection Jn is not empty. What does it mean? There exists a real number x in R so that x belongs to Jn for all n. Okay, but one can say something more if you assume further. Okay, if we further assume length of Jn, which is by definition Bn minus An, okay, this sequence of real numbers goes to 0, then intersection Jn, okay, is singleton x. That is, there exists an x in R, and so that x belongs to Jn for all n, and if there exists a y also in R, so that y belongs to Jn for all n, then x equal to y. So there is a unique x so that this happens. Okay, so pause, review, proceed. So what do we have? So the important thing is intersection of the Jn's as non-empty. Okay, that this gives an idea how, that is, if you are looking for a real number which is a solution of some problem you are looking for, what it says is look for a sequence Jn of closed and bounded intervals. Okay, and it's very likely to be there. Okay, this is very vague, but keep that in mind. This is the trick which you are going to use. So let us first prove the result we want to prove is the so-called Bolzano-Weierstrass theorem. This is the first application. What does it say? Suppose I have sequence xn of real numbers, right? Let us assume it's bounded. What does it mean? There exists an m so that for all n mod xn is less than or equal to n, right? Then the Bolzano-Weierstrass theorem says there exists a subsequence x and k such that x and k converges. Okay, so this is the result we want to prove. So let us recall what is meant by a subsequence. That is, there exists n1 less than n2 less than nk etc. nk plus 1 etc. Okay, for each k, nk it must be less than nk plus 1. Then let us look at k going to x and k. Okay, this sequence is called a subsequence. Okay, so we have to produce a subsequence which also converges. See, notice that the original sequence may not be convergent, right? For example, this is a standard thing all of you know, 1 minus n plus 1. Okay, this is alternating sequence. This is bounded but not convergent. Okay, but what the theorem says is I can still find a subsequence of this which is convergent. Okay, right. Now we want to prove this result. Yeah, I screen share. Okay, how do I do that? Okay, so the first thing is, let me look at x of n. Remember, when I say sequence, it's a function from natural numbers to R, sequence in R, right? Therefore, x of n is the image of this function. Okay, this is, loosely speaking, this is set of all real numbers xn as n varies over n. Okay, that is, okay. Now notice that the sequence is an, if you want to think of it as an infinite tuple, but this could be a finite set. For example, alternate sequence which we did, minus 1 to the power n plus 1, this sequence, my x of n is only 2 elements plus or minus 1. Do you understand? So this could be a finite set. Please understand this. Okay, so we want to put two cases. Case 1 is x of n, the image of the sequence, is finite. Say x of n equal to, let us say, alpha 1 to alpha k. Okay, alpha, of course, alpha j's are real numbers. In this case, for example, in the alternative sequence, the k equal to 2 and alpha 1 may be 1, alpha 2 may be minus 1, right? Now let us look at the sets S, J for 1 less than equal to J less than equal to K. Let Xj be, okay, the set of n, the natural number, so that Xn, that is the nth term of the sequence, is alpha j. Right? For example, in this case, my if alpha 1 equal to 1, and if I am looking for S alpha, okay, S1, this is alpha 1, right? S1. What will be this? This will be all even. Okay, indices. Set of all even indices. Right? That is 2 times n. Sorry, odd, sorry. Okay, odd. Because I start with 1, minus 1, etc. Set of all odd indices. You understand? As an example. Okay, now these are all subsets of n, right? Now you notice that Sj and Si, if I is not equal to j, these are disjoint. Why? Because remember, if some n belong to Sj intersection Si, what does it mean? Xn is alpha I, which is equal to alpha j. Okay, but now I am assuming I is not equal to j, therefore alpha I is not equal to alpha j, but Xn is what? X at n. That is the, okay, but x being a function, okay, it cannot take two values at the same point n, right? Therefore I am, okay, then there is no such n. You follow this? Make sure you understand this logic. Therefore what do I have now? I have n is union of Sj, j equal to 1 to k, right? Now n is an infinite set, okay, and Sj is a finite collection of subsets, right? So there exists at least one j so that Sj is infinite. Why? If all Sj's are finite, that would mean the union, finite union, right? Union or finite sets, okay, this will be finite, but that is equal to n, okay, because you give me any n in n, then xn must be alpha j for some j, right? Therefore that n must be in Sj. You understand why this equality? We know this is contained in n, but n is also contained in n, so these are equal. Okay, right. So therefore let j be such that Sj is infinite. So this is an infinite subset of natural number. Therefore this is not empty. In particular Sj is not empty. Okay, that cannot be empty anyway. We know that because alpha j is a value taken by x. Therefore there is at least one n such that xn must be alpha j. Okay, but just because infinite. Why I am saying infinite? I can use well ordering principle. What does it say? If S is a non-empty subset, then there exists an x in, or let me call it m in S, so that m is the least element of S. That means that is for all n in S, m will be less than or equal to n. M belongs to S and m is less than or equal to n. Okay, so I want to make use of this. Now Sj is not empty, right? Therefore there exists, let us call m1, if you want to call it n1, the least element of Sj, right? n1. Okay, now let's look at Sj minus n1. Can this be empty? No, because if it is empty, Sj must be singleton, but Sj is an infinite set, therefore this is not empty, and this is again a subset of natural numbers. Therefore there is an n2 in Sj minus n1, so that n2 is the least element of Sj, right? And what is the relation between n1 and n2? n1 is less than n2, because n1 is the least element of Sj and n2 was already there. Therefore I know n1 must be less than n2. You follow that? Right. So by induction, assume n1 less than n2 less than nk are chosen from Sj, right? Now let's look at Sj minus n1 etc. nk. This is a finite set, this is an infinite set, therefore this is non-empty. Therefore again there exists least element n k plus 1 in Sj minus n1 nk, right? And by our assumption, this is clear because nk plus 1 belong to Sj minus this set, therefore nk plus 1 must be greater than nk. And by induction, we had already chosen n1 less than n2 less than nk. Do you follow that? So make sure that way I constructed a sequence xj. Okay, right. Now let's look at the sequence xn1. What is that? See, for each k, nk belong to Sj, therefore xnk is alpha j, right? Therefore xnk is the constant sequence alpha j, right? This is not j varying. You understand that? Constant sequence, that is xnk equal to alpha j for all k. Therefore xnk converges to alpha. So thus we have proved if xn is finite, okay, if we have found a convergent subsequence. Okay, please go through the proof and understand. So case 2, we will assume x of n is infinite. Okay, this is where we will use nested interval theorem. Okay, so what is the idea? So as I said, so we are by assuming xn modulus is less than or equal to m, that means xn lies in the interval minus m to plus m for all n, right? So what is the trick? So I want to show I can find a subsequence which is convergent, right? So if it is convergent, there has to be a real number which is a limit x, right? So how do I find that x? So I'm just working backwards, right? Suppose x and k converges, then it converges to a real number x. So this x I am going to find intersection of Jn, where Jn is a nested sequence of intervals which is going to be built out of this. Just have an idea so that you will see what we are doing, why we are doing. Okay, so now let's look at this interval minus m to plus m. Okay, this is a trick which is usually called bisection method. In classical books they will call it bisection method. Okay, split it in two parts, call this as j1. Okay, now I have interval minus 1 to 0 union 0 to m. 0 is common, but don't worry about that. Okay, now your x of n, this is contained in this is an infinite set, right? Therefore if I look at x of n intersected with minus m to 0, okay, and union x of n intersect with 0 to m, this is equal to x of n, right? Now this is an infinite set, therefore either this or this must be infinite. You understand that? Maybe both are infinite, I don't care, right? So at least one of this is infinite set. Okay, call the corresponding subinterval as j1. So if this is infinite, my j1 will be this. If this is infinite, then I will call this as my j1. If both are infinite, make you some choice. It doesn't matter. Call one of them. Okay, fix one of them. Fix one of the subintervals. Okay, so how will I write it? So fix one of the subintervals that contain infinitely many terms. Infinitely many terms of many terms xn. So what is my j1? j1, this is going to be a subset of minus m to minus m to plus m. This is subinterval. Okay, and with what property? Okay, that is the set n in n such that xn belongs to j1. This is an infinite set. It will simply mean there exist infinitely many terms of the sequence xn. See, I'm trying to be very careful how to learn to write such things, because I don't want to say infinitely many xn's. Okay, it may turn out my xn's may be the same also. Okay, try to understand. We will see explain all these things later. Right, for example, suppose I take a sequence of this kind. No, let's not worry about it. I don't want to look at that. Okay, is this all right? Oh, do you understand this? So if you have a problem, please take some time, understand. And what do I know about length of j1? So first, j1 is a subset of, oh sorry, call it j2. See, since I already called it as j1, this let me call it as j2. So notice that j2 is contained in j1, and length of j2 is half of length of j1. Right? Now this is j2. Now call it something a2 b2 if you want. Okay, it may be minus m to 0 or 0 to m, but let's not worry about it. Right? Now what do you think I should do next? I said bisection method, right? So what should I do? Again, put a middle point, take the midpoint, and consider this and this. Okay, j2 is subdivided into two subintervals of equal length, right? You understood that? Now let's look at, now j1 contains infinitely many, right? Infinitely many xn's. Therefore one of these, either a2 to, if you want to call it c2, either a2 to c2 or c2 to b2 must contain infinitely many xn's. You understand? If both of them have only finitely many xn's, then their union will also have only finitely many xn's, but that is x1. Are you following? If you again want okay, j2, this is j2. Okay, again if you want, call it j21, j22 if you want. Okay, then what do I have? The set of n in n such that xn belong to j21 union n in n such that xn belong to j22. This is set of n in n such that xn belong to j2. Do you understand this? Okay, this kind of careful way of writing is never explained. You just intuitively say one of them have infinitely many elements and keep going, but you should be trained to write things much more precisely. You follow that? This is an infinite set, and it won't, any n should be in one of them. It may be in both also, because the common point may be in both. Okay, it may be only xn, so it may be. Are you following? Try to think, don't get, see, the point of my lecture is to make you think, understand. Okay, don't worry about whether you will be able to write it, etc. Learn that, it will make you think properly. Okay, we follow that. Therefore this is infinite set, therefore one of them must be infinite, so call that as, so one of this is infinite. Okay, call the corresponding subinterval as j3. j3. Now what do I know about j3? j3 is contained in j2, and length of j3 is half of length of j2, therefore it is 2 to the power minus 2 length of j1. Yeah, so understand this. try to learn this kind of abstract way of writing so that you know how to turn something what we vaguely say J to contain infinity many extents etc. We are making it very precise. A professional mathematician may learn to write like this. Okay, so now let's move by induction. Therefore, by assume by induction, we have J1 contained in J2 etc. contained in Jk, so that the set of all n in n, so that xn belong to Jk is infinite, and this is 1, and 2, length of Jk is length of Jk minus 1, therefore it's like this 2 to the power minus k length of j, which is 2 to the power minus k into 2m, but that's immaterial, that's not J1. Yeah, okay. Let me see, J2 was length of 2 to the power minus 1, therefore I should be very careful, therefore it should be minus k plus 1 if you want. Yeah, alright. You follow that? Because J3 is length of J2 by 2, therefore it's 2 to the power minus 1, and length of J2 is 2 to the power minus 1 of length of J1, therefore 2 to the power minus 2 length of J1. So there is always this kind. Okay, right. Do all of you understand? Now once I have Jk, call it AK, Bk. Okay, then I know by this is an infinite set, therefore I can again bisect it. AK, Bk, middle point is Ck, right? Therefore the set of n in Jk, so that xn belong to Jk, sorry, set of n in n, so that xn belong to Jk, this is equal to set of n in n, so that x belong to AKCK, union set of n in n, so that xk belong to ck bk, right? And this is an infinite set, therefore one of them is infinite, therefore call whichever set, if both of them, choose one, jk plus 1 is bound. Okay, so by induction I have a sequence jk, so that what happens, jk plus 1 is contained in jk for all k, and 2, length of jk is 2 to the power minus k plus 1 into length of j1. Okay, and 3, the set of indices n, so that xn belong to jk is infinite. So notice that the third, what is the intuitive way of saying? Infinitely many terms xn lies in the interval jn. Okay, please understand. 3 means infinitely many terms of the sequence xn lie in jk. Is that all right? Okay, now we are ready. See, now therefore jn jk is a sequence of nested sequence, so apply nested interval theorem. Therefore there exists a unique x in intersection jk, that is for all k in k n, x belong to jk. Maybe if you want, call it ak bk. Yeah, now what do you think I want? I have to find a subsequence, right? So I want to find a subsequence which converges to this x. How do you think I will find? So choose, see, now let's look at j1, right? The way I chose my j1 is there exists infinitely many right? Therefore I can choose let n1 be in n so that j1 contains infinitely many xn's, right? So let n1 be such that xn1 belong to j1. Remember my j1 is minus m to m, therefore my x1 itself will belong, but let's not worry about. Okay, I usually would call j0, but I forgot. Okay, that doesn't matter. It's not going to affect our proof, right? So for now, suppose look at j2, right? j2 contains infinitely many n. That is set of, again if you want you have to be careful, xn belong to j2. This is infinite. This is an infinite subset of natural numbers, right? Therefore there is an n2 here, so that n2 is strictly greater than n1 because the infinite set, right? If it is not true for each n here, n will be less than or equal to n. Okay, if false, try to learn to think. Okay, if false for each n in this set, okay, n must be less than or equal to n1, right? Therefore what does it mean? This set n in capital N, so that xn belong to j2 is contained in this set 1 to n1. This is a finite set, therefore this cannot be infinite. Do you understand? Okay, don't work simply on intuition, accept it on faith. Okay, so it may be tougher than what you see in your classroom, but you will learn how to think carefully and critically. Are you following? Right. So now suppose I have chosen n1, n2, nk, so that xn I belong to jni for each I, for one I less than or equal to k, right? Now let's look at jn plus 1, k plus 1, right? Now again the same trick. Let us look at n in capital N, so that xn belong to jn k plus 1. This is an infinite set, right? Now let's look at n1 less than n2 less than nk. Okay, right? Now this is a finite set, this and this is an infinite subset of natural number, therefore there exists an nk plus 1 which is greater than n1, nk, and hence greater than all, right? This belong to this set in such that nk plus 1 belong to this. Do you understand this? Please understand carefully. Therefore I have chosen by induction, we have chosen indices, a sequence of natural numbers n1 less than n2 less than nk less than nk plus 1 and so on. With what property? Each s and k belong to j and k for all k in n. Yes? Okay. Make sure you understood. So now x and k is a subsequence. Yeah? Because n1 less than n2 less than nk, that's an increasing sequence of natural number. The corresponding terms are what I am looking at. Therefore this is subsequence of the original sequence xn. Now I claim x and k converges to x. Yeah? How do I prove that? So the picture may be helpful here. Let us do, this is x minus epsilon, x plus epsilon. So let epsilon positive be given, right? Now remember my x belong to jn for all n. If you want jk for all k, yeah, jk for all k, right? Okay, and what is the length of jk? Length of k is minus 2 to the power k plus 1 into length of j. This is j1, this is finite, that goes to 0 as k goes to infinity, right? You follow that? Yeah? Okay. So I claim there exists n natural number n, or maybe since I want a, what I'm using, I'm using a k, and let's be okay. There is a natural number n, so that okay, for all k greater than equal to n, jk is contained in x minus epsilon to x plus epsilon. How do I do that? Again, instead of saying choose capital N like this, let us try to find out. Suppose I start with the y in jk, right? So if I want to say y belong to x minus epsilon to x plus epsilon, what does it mean? That means I have to say mod x minus y should be less than epsilon. Yeah, right. Now remember, x belong to jk and y also belong to jk. You understand? Therefore, what will be mod x minus y? That will be at most the length of jk, right? This is my jk, ak, bk, and my x and y are somewhere here. Therefore, the maximum possible distance for this will be at most jk, which is 2 to the power minus k plus 1 into length of jk, which is we want make it everything 2m. Therefore, it is 2 to the power minus k plus 2m. Yeah, right. So I want, this is the maximum, so I want this to be less than epsilon. Therefore, what choose n, so that 2 to the power minus n plus 2, that is 4m, is less than epsilon. That is 2 to the power minus n is less than epsilon by 4m. Yeah, can you do that? Please understand. Okay, hence if k is greater than or equal to n, my j and k will be contained in x minus epsilon to x plus epsilon. Remember, n1, n2 is greater than n1, n1 is greater than or equal to n, therefore n2 is greater than or equal to 2. By induction, suppose nk is greater than or equal to k, then nk plus 1 is greater than or equal to nk, but that is greater than or equal to sorry, it's strictly greater than nk, but that is greater than or equal to k, therefore nk plus 1, it's a natural number which is strictly greater than the natural number nk, but that is greater than or equal to k, therefore nk plus 1 at least be k plus 1. You follow that? Therefore, if k is greater than or equal to n, okay, what do I know? J and nk will be greater than or equal to n, because nk is greater than or equal to k, that is greater than or equal to n, right? Are you following? Therefore, j and k will be contained in this, right? So what does that mean? So now we start with x and k, that is in j and k, therefore x and k lies in x minus epsilon to x plus epsilon. This is true for all k greater than or equal to n. Yeah. So you gave me an epsilon positive. I found a natural number n, so that for all k greater than or equal to n, I found x and k lies in x minus epsilon to x plus epsilon. That means x and k converge to x. Thus I found a subsequence which converges to, which is convergent. So please go through it. If you are a BSc student, okay, you will see the way I dealt with the various things may look little more demanding and abstract than very loosely saying there is infinitely many and therefore this must be etc etc. Okay, we nailed it down carefully, okay, by writing proper notation. Okay, learn that well, and this is the way you will appreciate how to the kind of intuitive idea how to turn it into rigorous mathematics. Okay, we will meet with another application in the next session. Okay, I hope you all enjoyed. Stay safe.